lot for now staying over time, actually. I really appreciate you're still here. Thanks to Adam, you already had a very nice crash course into privacy preserving machine learning. Now we're going a bit more into detail into one line of work that we actually developed from scratch in our lab and that I'm actually very excited about. It's about machine learning with individualized privacy. And I don't know about you, but I personally generate a lot of sensitive data by text, by taking photos, doing online banking. And I do so basically to do my own services or to contact my own family or friends. But those are not the only ones who benefit from my data. But in reality, much of my data is just processed by large companies. And why would the companies do that? Well, because they want to offer us some better service. They want to, for example, give me better image classification on my phone, or better web browsing experience, or next word prediction on my keyboard. But this, of course, comes with a lot of privacy concerns. So the concern that my private data leaks, Adam showed basically that there are attacks that can really harm the privacy of my data. Now, there is one problem about it. When I talk about privacy, when Adam talks about privacy, or when any one of you talks about privacy, we don't necessarily mean the same thing. But some people are very much concerned about some details of their data, whereas others just have some weaker preferences. Others potentially don't care about privacy at all. But the whole field of privacy preserving machine learning, since it came up in 2016, has basically run this idea of epsilon delta differential privacy that you saw today with Adam. And the limitation there is that even though everybody of us expresses that we have different preferences for privacy, when we train machine learning models, every one of us gets the same level of privacy. And of course, if we want to find one level that fits each and every one of us, we always have to comply with those promised privacy preferences that are encountered among all of us, because otherwise we would just overgo some people's preferences. So the stronger the privacy preferences are, unfortunately, the more noise we need to add to the private training. And this, at the end, the more noise we add, the more we blur our signal, and the worse our model predictions come at the end. So if we need to comply with the strongest privacy protection in the whole data, then we have at the end a bad model, which impedes oftentimes privacy preserving machine learning from being applied in practice. So we sat down and we thought, this is actually not how it should be, but we should be able to overcome both limitations at the same time. And this is the aim of this line of work, where we basically want to adapt privacy preserving machine learning such that instead of having one privacy level for a whole data set, we can have a privacy level per individual in the data set. And what this nicely brings with that is that at the same time, we improve the utility of the final model because we can just learn a bit better from data. And today I'm going to give you a walkthrough through all possible aspects on how we can achieve differential privacy. Just to start on a high level, again, you saw the low level, but just differential privacy in machine learning tells us that if we have two data sets that are neighboring, so they only differ in one data point, then they give us roughly the same privacy level. They give us roughly the same machine learning model. And here it shouldn't matter whether the model differs in this data point or in that data point. So you can see always in the upper row it's included, in the lower row it's not. Now the problem is that these data sets in which the training data could differ potentially, they obtain in the private training the same privacy level, even though the one individual expresses they have very strong preferences, and the other one expresses that they have weak preferences. So what we now aim to do is to go from the universal privacy level over a whole data set to individual levels. So we want to move from one epsilon differential privacy to multiple epsilon differential privacy, in the best case, or in the most desirable case possible, to have one epsilon per data point. And we have a line of work basically on that, covering all the two standard machine learning frameworks, starting with the Pate framework and then going on for the differential private stochastic gradient descent framework. And I'm going to walk you today through the algorithms. I'll leave you with the privacy analysis and the theoretical guarantees for the paper if you're interested. But just to give you an understanding on that it is relatively intuitive, but then in the details and the nitty-gritty gets tough to get individuals the privacy they want. So let's start with the Pate algorithm, because that's the one that's hopefully still the freshest in your mind. Just as a quick refresher, and because I would like to show the algorithm to you also in the context of just standard machine learning training and not prompt training, let's recap how it was with Pate. So we had that private labeled data that we split in disjoint sets. And then what we do, in contrast to large language models, is we don't take a model and prompt it, but we just use really these data chunks as training data for individual models. And this can be all kinds of models. Not each of them needs to be a neural network, can also be decision trees, SVMs. You're free. They can even be any type of model that you want. The important thing is that each of these individual teacher models then is trained on this disjoint chunk of training data. Now, the problem is, because those models have seen this training data and because there are attacks like the membership inference, we can just not publish this whole ensemble. So we want to do some privacy preserving knowledge transfer. And how we do that basically is, like Adam already showed you, with some public data. And this public data is usually unlabeled. And how we obtain basically labels from that is through the teacher. So we take one by one the data points from the query set, and we get a histogram on the votes from the different teacher models. Now, the good thing is, in terms of privacy guarantees, each teacher can only alter 2 votes, because if it votes for one class instead of the other, the vote count for one class decreases, the vote count for another class increases. So this basically bounds the influence that also by transition each data point can have on this vote histogram, and leaves us with a relative limited amount of noise that we have to add to basically hide the contribution of each teacher. So imagine now we have added the noise. What we do then is that we take the argmax of all these votes, and this argmax then basically gives us the label for this public data point. And now we have data and we have labels. And what we then do in classic machine learning is that we just train a student model. So basically they just get this data set and they are trained. And because they never have seen the private data, and because this knowledge distillation, so to say, has taken place with privacy guarantees, so with noise addition, the student model at the end can be released and it can be queried an infinite amount of time without leaking additional privacy. So let's think about now how we can individualize the privacy guarantees here. And I think I gave you a rough intuition on like where the privacy stems from. It's first of the fact that each data point can only be in one teacher. And then by the fact that each teacher can only influence 2 votes. Like this basically limits the influence that each data point can have on the outcome, and gives the privacy guarantees. So to individualize these guarantees, we identified 2, please.
Are the teacher models different? And if so, where do they come from?
So you can initialize the teacher models as you like. Like in the simple case, just initialize like always the same small, like CNN, for example. And then you have your private data split in different chunks, and you train each teacher on its own chunk. And then they are trained, basically.
Are they trained in just standard supervised manner? Or okay, on different sources of the data?
Exactly.
Can be also same architecture in this case.
Yeah, can be.
But
Exactly.
can be also different architecture. Can be like decision trees, neural networks.
Just any.
Cool.
And so the 2 points where we now actually can get some individualization here is in the point where we distribute the data to teachers, and in the point where the teachers eventually vote. So where we aggregate basically what the teacher. And let's dive more deeply into that. So the first one where we look into the data distribution is our new method that we propose. It's called upsampling. And beforehand, the impact of any individual point was kind of limited because it can only influence one teacher and one teacher's vote. But what we now think is that if a data point, or a data owner in this case, is ready to give up more privacy, it should be okay that their data point influences more teachers, and thereby basically they contribute more information to the whole process, but also leak more privacy. So the core idea of our upsampling method is basically that we, instead of having the data point only once, we duplicate the data point and we give it to multiple teachers. So by that, basically, the teachers at the same time have more training data, which improves their utility, but also this data point leaks more often because it influences the votes of multiple teachers. And at the end, basically, you get then the privacy guarantee for this point, that is determined by the number of how often you duplicate the point. So if you have more duplicates, basically more teachers are influenced. And then they learn more from the point and the point loses more privacy, but also helps to get better utility.
Intuitively, it's a linear relationship.
Yeah, that's correct. The other part where we identified as a method basically to improve our individualization was what we called our weighting method. And imagine now we have standard Pâté again, so each point is only in one teacher. But now some teachers don't necessarily need to vote with the same number. Like before, every teacher has the right to vote once. And as I think data point, the public one is this and that label. And I give one vote for that. But now what we could do is that if a teacher holds data points that are ready to lead to more privacy, then they could just influence this vote count more. So what we basically proposed was to split the data into chunks according to their privacy preferences. So all that have like strong privacy preferences, they stay together. The ones with weak privacy, they stay together. And then the teachers hold data points that have individual privacy preferences. And according to the privacy preferences of the data points, the teachers then get more or less votes. So for example, the data points that have very strong preference, they still are only like in one vote included. But if a data point basically doesn't care, then its corresponding teacher can give many votes. So basically the final label incorporates more information from this data.
Doesn't make the teacher model any better as opposed to the previous method.
Exactly. Yeah, the teachers themselves, they do not become so much better, but what observe in general. So even like with weak individual data points, we have a relatively good ensemble usually. So it's like when I present the results, you'll see that they are roughly on par, both methods. So we don't necessarily benefit from having like one or two really strong teachers, but we just get our benefit of utility over the whole ensemble.
How does that influence? Like it seems conceptually similar to bugging and boosting, all the ensemble methodology. How does it influence the final performance of the models? Because I understand the privacy implications. It seems from boosting that if you keep on bugging, like repeat the samples, that also influences the final results in terms of performance of those models.
Yes, we observe actually an increase in the performance through our method. So we at the same time get two benefits. We implement the preferences of the individuals and we get better final models at the end.
And what is like the difference in performance between the entire model? Like if you just take the entire data set without splitting, and if you split it into a number of models trained on separate...
I'll show a slide on that in like two.
It's more like Pâté question.
Oh yeah,
it's more like a Pâté, but then it kind of gives you the spectrum of performances where you operate, right? It's
like for Pâté, it usually depends on the data set and on your hyperparameter tuning. How many teams you have, like by how much can you split your data?
I think for MNIST it's very small difference, but for Spartan it's visible. Like 20%.
Oh, right. Okay, so it's
what if those groups of average, strong, and weak preferences are like extremely unbalanced?
In this case, what we do is we basically we give them to the next stronger group, because it's always okay to give individuals more privacy than they want because they're still protected. So let's say you have very small individuals with weak privacy preferences, then we just mix them into the bucket with the average one. And
we should mention that the main performance comes from that we leverage this privacy guarantee. Learn more models.
Right. So at the end, like just to compare our two variants, we have the upsampling variant, which is very fine-grained because each data point can be upsampled a different number of times. And this gives us basically per point guarantees. But what we need to do is we need to train Pâté in the central setting because the data points are shuffled between different teachers. For the weighting, we have a bit more coarse-grained privacy guarantees. And the privacy is basically per teacher. However, we can even apply that in a decentralized setting where you can imagine multiple hospitals. Each of them trains one teacher basically on their own data, and then they just aggregate their votes. So this is even suited for a decentralized learning. And just to give you a bit more insights into the privacy analysis of our variants, we have to do here with Gaussian mechanisms. And in a Gaussian mechanism, what we do is basically we just add Gaussian noise to our results. And here we add the Gaussian noise to the vote count histograms. And the noise scale is basically given here by our application. It's a hyperparameter. And the sensitivity is like how much can each data point influence the method that we have. And the sensitivity in that case is determined really by the method that we implement. And what has been shown in theory is like in a form of differential privacy, which is called RDP, where basically instead of the delta that you saw with Adam, you have an alpha, that if we have a Gaussian mechanism, it gives us these form of privacy guarantees that basically depend on the sensitivity, so how much each data point can change the outcome, and then on this alpha and divided by the noise multiplier again. And just to give you a short overview on our methods is if we have standard Pathé, basically each teacher can influence the model by like the outcomes by 1. So one class can get increased, another one can get decreased. So it's a total sensitivity of 2. And so basically in this equation here, we plug in the 2 instead of this like sigma of f, and then basically it boils down to this privacy guarantee. And in the upsampling variant, because like now many points are in many different teachers, or the same point is in many different teachers. And so some get like different predictions, others get other different predictions, but the number of vote counts that are changed, they're really influenced by the number of how often we upsample the points. So the upsampling influences the sensitivity and thereby also gives us a different privacy bound. Finally, for the weighting, we don't have basically any teacher's vote changing more than before. So the teacher still can give its vote to one class or take it away from another. But then at the end, we just multiply its vote, like for example, by 2, by 3, by how often or how much weight we want to give that. So the privacy bound for this method actually depend on the weighting of the data point. Just to give you some small intuition on how that basically works in comparison with the standard Pathé, is that in standard Pathé, we always have to choose the smallest privacy guarantee that is in the data set. And here we have an example where we have 2 groups of private data points. The one which has basically a privacy preference of log 2 and the high one with log 8. If we train with standard DP, then we need to take log 2 for all of them. And we can see how many public labels can be generated before the privacy budget is exhausted for voting. And how many we get is 257. And this means that we would have 257 training data points for the student. In the case that we do individualized privacy, we have the high group, which could, if it was on its own, like answer basically 890 queries. And the low group could even answer 957. But because we need to make sure that all of the groups exhaust, like they stop basically when some data points have exhausted their privacy budget because it's still the same ensemble. So we need to cut off basically at 890. And then basically we have 890 training data points for the students instead of 257. And one big contribution of our paper was how to deviate basically the weighting and the upsampling for each individual data point. So how to find the good parameters such that the different groups exhaust their privacy budget at the same time. Just as a final thing, let me show you how much the individualized privacy improves the student accuracy of the final model. So what we see is that depending on how the groups are distributed. So here we show you a table basically where the baseline is always like log 2. All the data points have privacy budget log 2. And they get 88.7% accuracy on MNIST with Pathé. And then what we now do is we give to 25% of the data points, we give them a higher privacy, either log 4, log 8, or log 6. And we see that the utility improvement is already quite significant, with up to 5%. And now what we observe, the more data points basically get the higher budget, the more we can even increase the utility. So we see that if more data points in the data set are ready to give up a bit of their privacy, then we can boost the model utility. So I think we don't really have time to go through the second method, but I would invite you to, like, if you're curious about the concept of utilizing privacy more, to also check out our paper that we had this year in NeurIPS, where we do a similar contribution for the DP-SGD algorithm, which is way more standard. And therefore, I think is going to influence even more the practical application of privacy preserving machine learning. And there we also propose how to get privacy guarantees for individual data points. We evaluate empirically what this does for the utility. And then we propose mechanisms how to derive these individualized parameters. And I think that at the end, hopefully in the future, not all machine learning applications, when they introduce privacy, will give us all the same level, but really ask for our preference and then implement. If you have any questions.
Thank you so much. Yeah, that's. We have like one question so that we're still within time budget, not privacy budget. Any?
So I have a more general question. So I think like a lot of problems in privacy come from the fact that the model, they seem to like memorize like exact data of the training data, like on some data points. So I have like a question whether you see like some other research direction, maybe like designing better training procedures or changing architectures so they don't seem to like memorize so the specific some of those specific data points.
Oh, that's a very good question. So differential privacy by definition should avoid memorization because it tells you that whether or not a particular data point is in the training set, the model should be roughly the same. But this is a very strong theoretical guarantee. It also assumes that basically the attacker who wants to learn some private information knows the whole rest of the data set. Whereas there are some empirical methods also like early privacy machine learning research, like to battle membership inference. They use some techniques, I think, that are also used nowadays with against memorization, like early stopping or so, like very naive methods of regularization. And they showed that empirically, this also gives protection and this mitigates the attack. However, it doesn't give you any formal guarantee. And for privacy, especially with the legislations that we have in the European Union, often the regulators shout for utility, for guarantees. And this then basically has to be implemented with a much too rigorous framework, maybe.
Is there some other way of ensuring privacy that gives mathematical guarantees other than DP?
So I mean, there were some predecessors of DP, which all have been shown, like k-anonymity, etc. They all have been shown to fail in some scenarios. There are some relaxations of DP. So like right now that you have the whole bandwidth of we saw 2 today. We saw like this epsilon, or actually we saw 3, like pure epsilon DP, epsilon delta DP. Then I also introduced you to this RDP, which is just another form. And some of them have very like better properties in terms of they give you much tighter bounds and thereby allow you to have better privacy utility trade-offs. So they are more practical.
Yeah. So just out of curiosity, because you say that DP in effect like prevents memorization, right? So did you check, for example, if the networks trained with DP are, for example, more robust to distribution shift or perhaps even adversarial? Like...
Oh, that's an interesting question. So not in this line of work, but I have another line of work that studies the intersection between privacy and adversarial robustness. And there we find that actually these two are not necessarily aligned. The problem is that DP kind of hinders the convergence of your model. And with less converging models and like sharper minima and sharper optima, you get more vulnerable to adversarial examples. So there is still some open research on how to best combine the two of them. But I think that's a very interesting direction.